Okay, so naturally, when we go to get into rotational motion, we're going to have to follow a sequence. We're going to have to begin somewhere, and we are going to begin by describing the motion itself using kinematics. However, before I get into kinematics and before I start getting into all the different terms and all the different variables and all the different equations, I want to take a strong initial conceptual approach to rotational motion. I want to kind of go through the entire gist of the initial first half of rotational motion by just going through the concepts with you here right now. And so, for example, I want us to think of this not as a path, but as a platform. Think of it as almost like one of those rotating small merry-go-round type things that you see at a little park, or even a turntable, some sort of platform that's rotating around. This whole plate, this is a whole solid disc. And I'm going to have it so it's rotating in a counterclockwise direction. So I'm going to do a little swoopy here just to show the direction it's going. There's my little counterclockwise swoop, right? Counterclockwise, and then clockwise would be this way. Okay. And so this is just rotating. And I also want us to think of this as being on a frictionless surface. We don't have to worry about any sort of interaction between the rotating platform and the surface below it. We're just going to crank it, set it into motion, and then kind of think about what happens to it. Does that make sense? So maybe think of a little spinning top or a ball even that you can rotate, and we just want it to be spinning, right? Now, what I want us to do is think about just the general concept. So, for example, in the beginning, the platform itself, or the ball, or the top, or whatever you're thinking about, isn't moving at all. It's just kind of chilling there. So we can describe its initial motion right now. It's at rest. It's apparently in some sort of complete equilibrium. It's not moving, it's not translating or rotating. Let's discuss that real quick. Translating versus rotating. We're going to use those terms a lot in this unit. When we're talking about translate, we're really talking about more linear motion descriptors. When things go left or right or forward and backwards or out into the board or into the board, up and down, north, south, east, west, etc. It's translating, it's sliding, it's moving, but it's not changing its orientation, okay? And then we talk about rotational motion. We're talking about as it's rotating amongst a fixed point, okay? So translating versus rotating. So in this particular case, it's in equilibrium. It's just at rest. But then we take it and we give it a little spin, right? So we know there's an interaction there. My hand is coming to play and doing something to the object, then that object starts to spin. So then we got to think about what's happening to its motion between it being at rest to while my hand's in contact rotating it to after I've removed my hand from it and now it's in rotation. So what's happening in those three stages? So let's get to that last stage first. Once I've released my hand from it, I want you to think about the outside forces that would be acting on this platform. If my hand is no longer in contact with it, and we're not worried about it between interacting with the surface below it, so we're removing friction, this is an ideal scenario, describe the motion of that platform. So think about that first before I just start rambling on and explaining to you. Maybe pause it and try to think about just describing its motion. And I am hoping that you can grab that motion pretty quickly. So let's get into it. So after I released it, removed that force away, how can we describe its motion? We can take a couple ways. We can talk about its speed. We know it has some form of speed. We know if we were looking down from a top-down view, it's rotating in a counterclockwise sense. If I were to say make a dot on it as a reference point, right, that dot over time would be here, 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 and it would just keep traveling and eventually get back to where it began, and it's just going with some sort of speed. So once I've released my hand from it, what's true about that speed? Is this platform going to maintain a constant speed, or will that speed change over time? So for that, let's address maybe some of our laws of motion. We remember Newton's laws, and hopefully we remember his first law, the law of inertia. The law of inertia talks about an object in motion will remain in motion, or an object at rest will remain at rest, unless an unbalanced outside force acts on it. So it also references will remain in straight line motion. So that's where kids and students start to get a little mucked up. You're like, well, I know that if this was a particle on a friction-free surface and I pushed it and let it go, hopefully you recall it'll travel forward at a nice constant speed unless an unbalanced force acts on it. So what happens to this platform once I've let it go? It's not really traveling in a linear sense, so it's hard to rely on Newton's first law to know this concretely. Well, think about it though. If there are no outside forces acting on it, would there be any reason for it to experience a change in its state of equilibrium? Is it going to be having a net force, or is there going to be no net force acting on it? And hopefully you can conclude that once I remove my hand, there's no net force acting on it. And therefore, it should maintain its state of motion, and it will. This would be the first initial descriptor of what we will refer to as uniformly accelerated motion, but with rotational motion. We're dealing with a scenario in which once we released it, the acceleration here is 0, but even if it was something, it would be constant. And the motion will maintain its motion unless there's an unbalanced force, so it'll maintain a state of constant speed. So we have descriptors like angular speed that we've got to talk about. We got to talk about how forces act on it, and what happens if I applied my force from out here versus maybe in the middle in a smaller area. Would that change the ability for it to spin? And we also have to talk about terms like angular acceleration. But now let's also think about energy. Let's use the energy hat here. In the beginning, this thing was at rest. Then I twisted it, removed my hand, and then it starts spinning. So how does the energy change? Well, it goes from no energy in the beginning to some form of moving energy after I've released it. And yeah, moving energy still takes place here. It's still kinetic energy. Well, where did it get that energy? Where did it get that energy from? Sure, we can use dynamics, as we already did with Newton's laws, to describe the force acting on it. But we also can use energy to realize that when my hand came into play and I rotated it, I must have done some work on the system. I must have introduced energy into that system that came from this outside force coming from my hand. So how are we going to describe that? These are all the different bits that we're going to unravel throughout this course, and I have to refer to them throughout my even description on just standard motion or kinematics of rotational motion. So I'm going to cut the video right now just so I can get into my first kinematics lesson nice and fresh. Let's go.